Alrighty, guys. So pull up the workbook for Unit 9. If you were absent, sorry. It's the lecture is posted up on on YouTube. So you guys can check that out. But we're going to be continuing with bond polarity. So last time we met, we learned how to draw covalent compounds, where we draw the single, double, triple bond and whatnot to combine them to get or to connect the atoms. But when we have a chemical bond, there's something called bond polarity that we need to consider. Okay, now bond polarity basically just means how equally or unequally the electrons in a covalent bond are shared. Okay, so we learned last time that in a covalent bond, the electrons are shared between nonmetals, right? And so sometimes they share them equally, and sometimes they don't share the electrons equally. So there are two types. Let's talk about the one that's easier, non-polar covalent bond, non-polar. Okay, not polar. Okay, if the bond is non-polar, it means the electrons are shared equally. Okay, it's non-polar. And an example of a bond, a non-polar covalent bond, dang, that's hard to say, a non-polar covalent bond, it's usually going to be between two atoms that are the same atom. So if we have two chlorines, they're going to share the electrons equally. If we got like two nitrogens, they're going to share the electrons equally, which makes sense because it's the same element, right? They're two of the same. Okay, however, those are not the interesting ones. The ones that are interesting that we need to pay more attention to are polar covalent bonds. And you guys can probably tell it's just the opposite of a non-polar one. It's where one of the atoms holds onto the electrons more tightly. It has a greater attraction. Okay, there's a greater attraction for one of the elements in that bond. Okay, so a good example of this would be HF. Okay, if you have hydrogen and fluorine and they're bonded together. Okay, I'll just give you guys the answer right away and let's see if you guys can figure out why this happens. Okay, when we have hydrogen and fluorine sharing electrons, the polar bond or the polarity is going to go towards the fluorine. The fluorine is going to pull the electrons more tightly to itself. Okay. Anyone want to take a shot at why? Yeah, no. Yeah, so fluorine does want to gain one electron, but that's not the reason why, because here hydrogen wants to gain one as well. Yeah, Josh. So there are more protons than fluorine, but what do we call that? Remember, Great? Yeah, Molly.
There's higher electronegativity.
Yes, electronegativity is the term. Okay, fluorine is more electronegative. Dang, I could not spell. Okay, fluorine is more electronegative, right? And we learned last unit that electronegativity is basically how tightly the atom holds on to the electron. So if we have two elements that are sharing electrons, one of them is more electronegative. It's stronger, basically. And so it can hold the electrons more tightly. Okay, so when you have a bond, this symbol right here is kind of like a plus sign with an arrow on one end. The arrow points to the side that is more polar, okay? Basically where the electrons go. Okay, so here we have an example of a polar covalent bond. It's going to go towards the more electronegative one. Oh, I guess I gave you guys a hint too with electronegativity. Okay, but does that make sense? Whatever's more electronegative in a covalent bond, the side that's more electronegative is going to take more of the electrons. Okay. So if fluorine takes more of the electrons, is it going to be more positive or more negative? Yeah, so there's a symbol that we use to display that. What we're going to do is we're going to do a minus sign, and we're going to kind of do like an S, a cross between an S and an 8. Do you guys see that? This basically just means that it's a partial negative. Okay, and then same thing on the other side, the hydrogen is going to be a partial positive. Okay. And so even in a molecule where everything is balanced out, everybody has, complete shells and they're filled up, there's still going to be there could still be one side that's a little bit more negative because the electrons like to hang out more on that atom because that side is more electronegative. Okay. All right, any questions about that? Pretty simple? Okay. All right, let's try 9.9. So what I'm gonna do is I'm gonna give you guys a couple of compounds and I want you guys to figure out which side is the partial positive and which side is the partial negative. We actually did HF, so I'm gonna do something else with HCl. Okay, so we have 3 different compounds. I want you to draw all 3 of them, the covalent structure. And what I want you guys to do is I want you guys to figure out what's partially positive, partially negative. I'll do the first one up here just so you have an example. If you're confident, you can kind of ignore me and just finish this up. But if we draw F2, we have fluorine bonded to a fluorine. And here, they're both the same element. So this one is non-polar. So I'm just going to write non-polar. Okay. Now I want you guys to do the same. I want you to draw HCl and BCl3. And I want you guys to figure out if they have non-polar or polar bonds. And if it is polar, try to figure out where the partial positive and partial negative are. All right, I'll give you guys maybe 30 more seconds and then we'll go over it. Alrighty, guys, let's go over this together. If you're finishing up, feel free to do that, but I'm gonna start going over the problem. So we have HCl. So for the covalent structure, you should have drawn this. It's just a symbol, single bond between the hydrogen and chlorine. Okay, now if we take a look at these are different elements. So what we can do is we can figure out which one is more electronegative. So which one is more electronegative, hydrogen or chlorine? Yeah, chlorine is more electronegative, which means that the electrons are going to go towards the chlorine. And so there's going to be a partial negative on this side, a partial positive on this side. And so this compound right here is going to be polar. Okay. Hopefully that wasn't too bad. Any questions about HCl? Pretty simple. Okay. We're going to go to BCl3, which is a bit more complex. Now, if we're going to draw BCl3, we can see that B boron is going to have 3 valence electrons, and each chlorine is going to have 7, right? So 7 times 3. Okay, so if we add them together, we need a total of 24 electrons. Okay. Now, we're going to have B in the center because B is less electronegative, and we're going to have the Cl's around B. Okay, so we're going to connect them. Okay, and then what we're going to do is we're going to draw the valence electrons. So we want the chlorines to have 8. So we're going to draw 6 on this, 6 on this, and 6 on this. Now, B, if you guys notice, how many valence electrons does boron have? Yes, 6. So it does not have a complete octet, but you guys should have seen this in your reading, which we all do, right?
Yes.
Yeah, this time you guys did because I was out. But boron is very small, so boron actually doesn't have to have an octet. Boron is happy with 6. So hopefully you guys were able to recognize that. Okay, so this is the structure for BCl3. Now, which one is more electronegative, boron or chlorine? Yeah, chlorine. And so what's going to happen is the electrons are going to want to go towards the chlorine, right? And that's going to happen for every single one of the chlorines, okay? And so which one is going to have the partial negative, boron or chlorine? Yeah, chlorine. Okay, so each chlorine is going to have a partial negative, and boron is going to have a partial positive. Okay. Okay, so thank you. So if we take a look at the B and the Cl bond, is it going to be polar or non-polar? Yeah, so it's going to be polar because one side is partially negative and partially positive. So I'm going to make a little note here. The bond between boron and chlorine is going to be polar. Now, if we look at the whole molecule, though, is the molecule polar or non-polar? It's kind of weird, right? Because we have more than one element now. So I'll give you guys the answer. The entire molecule is actually non-polar. Okay, anyone want to take a shot at why? Yeah, great. They do all have 6 electrons on all the corner, which makes it partially negative. And that actually does contribute to non-polarity because polar means that one side is kind of positive and one side is kind of negative, right? So if we look at the bond, one part of the bond is negative and one part of the bond is positive. But if we look at the molecule as a whole, what's the partial charge on the entire surrounding area of the molecule? Negative, right? That means that this entire molecule, if you just look on the outside, is negative. And so what that means is that the molecule as a whole is non-polar because there's only a partial negative around it. There's no side that has a partial positive. And so even though the BCl bond is polar, the molecule itself is non-polar. Okay. That one was kind of a trick question. And I know it's a little bit confusing, but do you guys have any questions about that? Okay. In order for the molecule to be polar, basically everything around the molecule has to be, one side has to be positive and one side has to be negative. Okay. And we'll go more into that as we learn about molecular geometry. But any questions? Okay, we'll do 9.10. And I want you guys to try this one out on your own. You can work with the person next to you. I'll give you guys a minute to try solving it out. But there are 3 different bonds, S and Cl, S and Br, SeCl, and SeBr. I want you guys to figure out which one is the most polar. They're all polar, but which one is the most polar? All right, maybe 20 more seconds, and then we'll go over it. Alrighty, guys. So let's go over 9.10. So before we answer the question, if we just take a look at polarity, what did we say causes polarity in a bond?
The difference in charge.
Yeah, so not difference in charge, but the difference in electronegativity, right? So the difference in electronegativity between the atoms involved, that's what causes polarity. That's what causes one side to be more positive, one side to be more negative. So if I want to figure out which one is the most polar, I want to see what the biggest difference in electronegativity is, right? Because the bigger the difference between the electronegativity, the bigger the difference in the polarity, because it'll cause the electrons to shift more towards one side than the other. If it's kind of the same, then they're gonna shift a little bit, but it's still gonna be more evenly distributed. So let's go to look at SCl, SBr, SECl, and SEBr. So if we take a look at our periodic tables, we'll see that S is right here. So if we take a look at sulfur and chlorine, okay, what do you guys think? Do you guys think it's pretty similar or? Yeah, pretty similar, right? They're right next to each other. Okay, so this one is probably not going to be that that polar. If we look at the next example, SBr, okay, is this more or less electronegative or polar than this right here? What do you guys think? Yeah, a little bit more polar, right? Okay, a little bit more polar. Okay, next we're gonna look at SECl. So if we take a look at Se and Cl, we have SECl. Okay. Do you guys think this is gonna be more polar or less polar than the first one? Yeah, this one is gonna be more polar because again, it's going to be a difference in the number of shells that we have. And then lastly, we have SEBr, and we already know this is probably going to be less polar because they're right next to each other. So the two options that we come down to are SBr and SECl. Okay. So what do you guys think? Which one do you guys think is going to have the largest electronegativity difference? Yeah, SECl. Why do you guys think SECl?
SCl is the most electronegative out of the choices. Much better.
That's a great answer. Yeah, Cl is the most electronegative of our options. And then Sc is the least electronegative of our options. And so they're going to have the biggest difference in electronegativity. So the biggest difference in polarity. Basically, this is the little kid, and this is the biggest bully, and he's going to steal his lunch money from SC.
I agree with that.
I am not speaking from personal experience.
Were you the bully?
Yeah, that's what I was going to say. Okay, so that's how you can find bond polarity. Alrighty, any questions about that one? Hopefully not too bad. All right, let us move on to the next section. So we already learned about how to draw them, indicate the polarity of HF or just anything. If it's partial, you can write the partial positive, or you can draw the arrow. On the AP test for the FRQs, either way is going to be fine. And when you guys are interpreting pictures, people use both of those symbols, so just make sure you're comfortable using them. Okay, now, one thing we do want to mention is that polar molecules, right? If one side is more positive and one side is more negative, they're going to arrange themselves based on the charges, right? Because we know that opposites attract. And so the positive side of one of them is going to be attracted to the negative side. And so what I want you guys to do is just really quickly, I'll give you guys only a minute to do this, but I want you guys to draw 3 HF molecules. And I want you guys to draw how they would arrange themselves based on their polarity. Okay. So you're gonna draw 3 individual HF molecules. And I want you guys to organize them, arrange the pictures based on how the molecules themselves would arrange each other based on their polarity. Okay, and if you guys forgot, the polarity is up here. One H is more positive, F is more negative. Yeah.
As in, like, they'll mix all together.
So when they're not going to mix in the sense that they're not going to like break apart and react. But if you had 3 of these molecules next to each other, how would they organize themselves? Yeah. Take a shot at it. I'll give you guys a minute to do that, and then we'll move on to the next topic. Yeah. Not bond, they're not reacting, just how they would organize each other with each other. Okay, let's actually just go over this. It seems like there's a bit of confusion. So we said that the hydrogen is going to be partially positive and the fluorine is going to be partially negative. So we have 3 different HF molecules. Okay. We know that opposites attract. So the positive and the negative are going to want to be next to one another, right? So if I have this HF molecule and I have this one right here, okay, which side of the second molecule is going to be attracted to the partial negative? Yeah, the H, the side that's partially positive. So the way they would arrange with one another is you could do it like this, right? Because one side is partially positive, one side is partially negative. The hydrogen is going to want to be next to the partially negative fluorine, and then the same thing right here. Or another way that you could have arranged it is you could have put HF like this. You could have had it like this because it could just rotate. And then we could have H with the F and the F with the H, and then so on and so forth. So you could have arranged them any of those ways, but just recognize that the side that's partially positive is going to try to go towards the side that's partially negative and vice versa. Okay, yeah.
You make a triangle.
Like this.
Yeah.
That's a very roundabout way to do it. I would say this is not the best way to do it because you're not maximizing the distance then between the negatives right here and the positive right here. So, I mean, yeah, but probably not the best way to do it. You're getting a little too creative. Yeah, let's keep it simple. That's what I'm wondering. He's just trying to get fancy with it. Look at this, doesn't even make sense.
What if it was just all the H's like in a group, like put H like in a triangle almost, and then you just connect the H's.
No, that's what I did. It doesn't work because my goodness, guys, why do we always do this? Why can't you guys just trust me? No, Molly, we're moving on. We're moving on.
I drew both.
Oh my goodness.
Like this instead.
That doesn't even work even more because all the H's are positive. All the positives are going to push each other away.
Oh, okay.
You guys are thinking too much, guys. The rule of thumb is stop thinking, okay? Thinking is for dumb people. Smart people don't need to think because they already know. Okay, be smart. Stop thinking. Probably didn't want to hear that, but okay. Just another term that you guys are going to want to know is that the magnitude or the amount of a molecule's polarity is called its dipole moment. You're going to want to get comfortable with that term dipole. Dipole just means polarity, okay? And we'll talk more about that towards the end of the unit. And same thing that you guys can assume, the greater the electronegativity difference, the greater the dipole. Okay, so the more electronegative one side is than the other, the more polar it is. The more polar it is, the bigger the dipole. Okay, that's just another term for polarity. Okay, so you guys don't need to memorize the exact number for dipole moment. You're never going to be asked, what's the dipole moment in HF? You're not going to have to know 1.82. To be honest, I don't know either. But you do need to know the electronegativity difference causes a bigger dipole compared to other polar bonds. Okay. Just be aware of that term because sometimes they use polarity, sometimes they use the term dipole, and then later we're gonna have to know dipole for another concept. But any questions about that? Okay, so dipole is polarity. Okay, so we drew Lewis structures for 2 or 3 or 4 atom molecules that are made of 2 to 4 atoms. But now we're going to be drawing molecules that are a lot bigger. Now for these bigger molecules, it can get a little bit trickier. So there are 5 tips that I want to give you that you guys can keep in mind. First thing you want to do is you want to sum all of the valence electrons. So basically you want to find out how many valence electrons all of the atoms have. So we're actually going to go through all these steps in a problem just so that you guys can see it being applied. So if we look at 9.12, if we want to draw the Lewis structure for C H2 Cl2, what we're going to do is we're going to start off by summing the valence electrons. So let's take a look at this. How many valence electrons does carbon have? 4. Okay. How many does hydrogen have? 1, and then there's 2 of them, so it's plus 2. And then how many does each chlorine have? Yes, 7. And so if there's 2 of them, we have 14. That means the total number of electrons in this valence electrons in this molecule are going to be 20. So that means that when we are drawing our molecule, we need to use 20 valence electrons total in the bonds and the lone pairs. Okay, next thing we're going to do is we're going to write the symbols for all the atoms, and they all have to be connected by at least a single bond. Now, we know the rules for organizing it, right? We know that carbon, or the least electronegative element, goes in the middle. So here we have carbon. So we're going to put carbon in the middle. Okay, majority of the time, carbon is going to be in the middle. What about the hydrogens? Do we put hydrogen towards the inside or the outside? Yeah, hydrogen wants to be towards the outside. So we got 2 hydrogens. So we're going to put 2 towards the outside. And then the most electronegative one is chlorine. And so we're going to put chlorine towards the outside. Now, it doesn't matter how you organize this. You can do this if you really wanted to. Okay, but we're going to do it this way right here. But the way that you organize them doesn't matter as long as you follow the rules. Hydrogens go on the outside, the more electronegative ones go on the outside as well. Okay, then we want to make sure that they're all connected by at least one single bond. So I'm going to draw single bonds between all of the atoms. Okay, carbon's in the middle, so we're going to connect them all with carbon. And then let's figure out how many electrons we used. Okay, how many electrons are used in one single bond? 2. So we used 2, 4, 6, 8. So we used 8. So now we have 12 valence electrons left over. All right, next we want to see if we completed the octets. That's going to be number 3. Everyone needs to make sure they all have an octet. So hydrogen only has 2. So this hydrogen is good. This hydrogen is good. Is carbon good? Yeah, because it has 8. Carbon has 2 here, 2 here, 2 here, 2 here. That's going to be 8. The only ones that are not happy are the chlorines. Chlorine has how many right now? 2, and it wants 8. So what we're going to do is we're going to use the rest of the electrons. So 1, 2, 3, 4, 5, 6, which makes this chlorine happy because now it has 8. It has 2 right here, 3, 4, 5, 6, 7, 8. And then we use 2, 4, 6, 8, 10, 12. So that's 12. And now we've used every single valence electron. So this is going to be a structure for C H2 Cl2. So is going to get a little bit more complex with these bigger molecules. And it does just take a lot of practice. So if you guys want, what you guys can do is go online and look up some problems for drawing these more complicated molecules. If you go on the AP website, there should be examples like that as well. Okay. Alrighty, I'll give you guys 2 minutes to try this one right here. HCN. Okay, number 9.13. HCN. It'll take about 2 minutes. You can work with the person next to you, and then we'll go over it together. HCN. All right, maybe about 20 more seconds. Alrighty, guys, let's do HCN. So first thing we want to do is figure out the valence electrons. How many does hydrogen have?
One.
One. Yeah. Okay, I was gonna say my Spanish isn't that bad. What about carbon?
Four.
4. That's cuatro. And then we have nitrogen, which is 5. So that means our total valence electrons that we're going to be using are 10.
Yes.
Now we want to start by making a single bond between everybody. Okay, so that means we use 2, 4. So -4 is going to give us 6. Now, if we look, hydrogen is good to go because it's 2. How many more electrons does carbon need? Yeah, it needs 4 more. Okay, and nitrogen needs how many more? Yeah, it needs 6 more. Now, if we take a look at this, carbon needs 4, nitrogen needs 6. But the thing is, we only have 6 valence electrons to work with. So I can't give them all to nitrogen because then carbon is still going to require some electrons. And so the best way to do this is to increase the number of bonds. So if we put another bond right here, carbon is now going to require 2 more because it has 2, 4, 6, and then nitrogen needs 4 more. And then so if we put a triple bond in here, that means everybody is going to be ready, good to go with an octet, because hydrogen has 2 electrons, carbon has 2, 4, 6, 8, and then nitrogen has 2, 4, and 6. Oh, and then we would throw in the second one right there. That'll get us to 10. Okay. So a lot of this is just practice. You just kind of got to get used to using the valence electrons and how to organize them. Just want to make sure everybody has their octet. Okay. Alrighty, let's do a couple more examples together. I want you guys to try, actually, I'll have you guys try both of these. We're gonna have a PCl3. Let me increase the size of that, PCl3. And I also want you to try this one, BrO3 minus, okay? To do 9.15 though, you're gonna have to have read to that part of the book. So if you guys didn't, it's okay, just do 9.14 and then we'll try 9.15 together in a bit. So I'll give you guys about 4 minutes to work on that. You can work with the person next to you, split it up if you want, and then we'll go over it together in just a sec. All right, guys, I'll give you another minute to try that out. Alrighty, guys. You guys ready to go? All right, let's try it out. So let's do 9.14 first. So if we take a look at PCl3, how many valence electrons does P give us?
Oh,
Yeah, you should get 5 because if you count the boxes till you get to P, to phosphorus, you get 1, 2, 3, 4, 5. Okay, so P is going to give us 5 valence electrons. We said chlorine is 7 already, and there's 3 of them, so that's 21. That means our total number of valence electrons will be 26. Okay, now we need to organize these elements now. Which one of these should I put in the middle? Yeah, phosphorus, easy reason, it's going to be the least electronegative out of all of them. So we're going to put phosphorus in the middle, and then we're going to put the Cl's around it. Okay, we want to make sure that we have a single bond in between all of them at least. And so we're going to put a single bond like this. That's going to mean that we used 6. And so we're going to have 20 left to use. Okay, now we want to make sure that they all have an octet. But let's start by putting it on the most electronegative elements, because those are the ones that are going to try to hold the electrons anyway, right? So how many electrons does each chlorine still need? 6. So we're going to put 2, 4, 6 here. That's going to be 6. Another 6 here means it's 12. Another 6 here is going to make it 18. So we used 18. So 20 minus 18 is going to give us 2. And if you look at phosphorus, how many does phosphorus need? 2. So we just put 2 more. And so there you go. That's going to be your structure for PCl3. Now, if you did it a different orientation like this, if you put Cl on the top, P like this, Cl here, like that, that's fine too. Basically, all you're doing is turning it, so that doesn't really matter too much. Okay, as long as your connections are correct and you have the correct number of lone pair electrons, you're good to go on that. Any questions on 9.14? Again, this just takes a lot of practice to get kind of comfortable doing it. All right, lastly, we have 9.15. Hopefully you guys were able to get that, but if not, that's okay too. This one was kind of tricky. So if we take a look at 9.15, how many valence electrons does Br give us? 7. How many does oxygen give us? 6. And then there's 3 of them, which is going to give us 18. And how many does the minus sign give us? 1. Good. Okay, so that means we're going to have 26 total valence electrons because we can do 7 plus 18 plus 1. I think I did my math right. Okay, that's going to give us 26. Now, we want to organize them. So which one of these should I put in the middle? Yeah, Br, because it's less electronegative than oxygen. So we're going to put Br in the middle, and then we'll put the oxygens around it. We want to start off by making sure that we have single bonds between all of them. So we use 2, 4, 6. Now we're at 20. Okay, we want to make sure that all of the oxygens get their octets first because they're the most electronegative. So we're going to put 6 on each one of them. Okay. So we're going to have 6, we're going to have 12, we're going to have 18. So 20 minus 18 is going to give us 2. Did I do something wrong here? You're looking at me weird. 7, 6.
Oh, I know. Because it's the Br is giving up 2 per oxygen.
What am I doing wrong here? 7, 6, 12, 18, right? 25, 26. Yeah. She's looking at me weird. How did you do it, Elaine? Oxygen should what? Right, because we should get 2, and then that's 26, and then we would put the brackets around it.
Yeah.
Right. Is this how you guys did it? Or am I tripping out? Elaine, are you tripping out?
Yeah, no problem.
I counted it right?
Yeah.
BR is 7, 6, 12, 18. That's 25, 26. Okay. 2, 4, 6 is going to get me to 20. 6, 12, 18. That's going to give me 2 left. I think it's good.
It just looks weird. Because like when you first do like one thing with oxygen, you usually have like 5, and then you have 7. But because BR is giving away 2 per oxygen, it's the octet of the oxygen. And then BR would be left with 1, but since it's another electron, it looks like that.
You know what? Google is my best friend. It's not what we get on Google. Yeah, Google doesn't like that. One sec, guys.
Does this compound?
Oh,
fit?
okay. Sorry. So this structure does work, but it's not the best one, and we're gonna talk about why. That's in the next topic. That's why I was tripping out too. Thank you, though. So it does work. So this is what you should have gotten based on what I taught you guys so far. Okay. So if you got it, you're correct. Okay. However, there are other ways to draw different molecules. So that's the topic that we're gonna get into next. So if we go down. We're gonna be looking at an example, I guess a simpler one to look at, to see that there are multiple ways to draw the same structure. Okay, so when you draw a Lewis structure, and we're describing how the electrons are distributed, we can draw more than one Lewis structure sometimes and have them all obey the octet rule. So if we look at CO2, this is how we traditionally draw CO2. But if you just want to do octet rule, this one on the right side works as well, right? If you look at it, oxygen has 8, carbon has 8, oxygen has 8. So this is following the octet rule. They're all following the octet rule. Okay, however, there's a way to figure out which Lewis structure is the best one to use. And that was kind of the issue we were having with the previous problem. Okay, that one is correct, but it's not the best. And the way that you determine which one of these is the best structure is we use something called the formal charge. Okay, formal charge. Okay, and the formal charge is the charge the atom would have if all the atoms had the same electronegativity. So I'll show you guys how to use this formula in just a second, but make sure you guys copy down this equation. And just to let you guys know, you're gonna have to memorize this because it's not on the AP handout, unfortunately. Okay. So take a second to copy down the equation, and then I'll explain how to plug the numbers in, and then we'll do some examples, okay? Just to let you guys know, this is probably one of my least favorite parts of chem, formal charge. It's really annoying to do. Just make sure you guys copy down that equation. If you guys really want to, underneath the equation, you guys can copy down these two structures, kind of separate them from one another because we will be writing underneath it. So if you guys want to do that, if you guys wrote the, the equation down early, you guys can do that. A formal charge is group number minus number of covalent bonds minus number of electrons in lone pairs. All right, so let's take a look at how to use a formal charge. So what we're gonna do is we're gonna use this equation to calculate the formal charge of all of the atoms inside of a molecule, okay? So I'll show you guys how to do it on the left, and then I'll have you guys try it on the molecule on the right. So what we want to do is every single one of these atoms has their own individual formal charge, and this equation allows us to calculate that. So what we're going to do is we're going to do it for this oxygen right here, okay? So the formal charge of this oxygen is the group number. Basically, how many valence electrons does it have? So oxygen is going to have 6 valence electrons. How many covalent bonds does oxygen have? Yeah, two lines. And then how many electrons are in lone pairs? How many dots? 4. Yeah, 4. Okay, so if we want to make it easy, group number is valence electrons minus lines minus dots. Okay, so you guys can think of it that way. Okay, so 6 minus 2 minus 4 is 0. Yeah, 0. So this oxygen right here has a formal charge of 0. Okay, let's move on to the next one. We have carbon. How many valence electrons does carbon have?
Wait, my brain
4?
turned off. Yeah, 4.
4? Yeah, count the boxes. How many lines does carbon have? 4. Yeah, 1, 2, 3, 4. Yeah, 2 double bonds, but 4 covalent bonds. I know it's getting kind of confusing now. And how many dots does it have?
None.
0. So what's the formal charge of this carbon? Yeah, 0. I know that word in Spanish. And then we have oxygen right here. If you notice, it's kind of the mirror opposite of this one. So this one is also going to have 0. So everybody in this structure has a formal charge of 0. Make sense how to calculate it? Okay, I'm going to give you guys 1 minute, and I want you guys to calculate the formal charge of everything in this molecule right here. And what we're going to do is, based off the formal charges, figure out which one of these structures is the better structure. If you want to split it with your partner, you can. Yeah, what's up? Yes, yeah. That means you're doing it correctly. Alrighty, maybe 20 more seconds. And then we'll take a quick break after this. And time flies with you guys. This is so much fun. Alrighty, guys. If you're finishing up calculating the formal charge, feel free to do that. But I'll start going over it. So if we take a look at this oxygen right here, we know that it has 6 valence electrons. We subtract the lines. There's 1 line, 1 covalent bond, and then we have 6 dots. So what's the formal charge of this oxygen? Yeah, -1. Okay, next we'll go to carbon. This one, if you notice, it's the same thing. There's 4 lines, and so easy way to say that it's 0. And then if you look at this oxygen, there's 6 valence electrons. We got 3 lines, so -3, and then -2. So the formal charge is +1. Now, the 2 rules that you want to know for formal charge, other than the equation, is that the better Lewis structure is the one where everybody is 0, or if that's not possible, the one where the most electronegative atoms have a negative formal charge. So if we take a look at these two structures, which one do you guys think is better, left or right? Left, okay? And it's left because of both reasons. Okay, we want them all to have 0. Left side, everything has 0. Okay, but the right side, if you guys notice, which one is more electronegative, oxygen or carbon? Oxygen is more electronegative, but here we have an oxygen with +1. We don't want a Lewis structure where the more electronegative has a positive formal charge. And so even though one of them is -1, one of them is +1, so that's going to make this oxygen sad. And so we don't want this right structure. So this left structure is better because of both rules. All right, make sense? It is. All right, so we'll take a 7-minute break. You guys can go to the restroom, get some water, stretch your legs, and then we'll come back and do this very fun thing of more formal charge. So we got 3 different possible Lewis structures for thiocyanate, NCS-. And what we're gonna do is we're gonna find the formal charge of everything inside that molecule, and you're gonna figure out which one of the 3 is the better or more dominant Lewis structure. Now I'm gonna make your life a little bit easier for you, and I am going to do the last one for you. Okay, so you guys just need to do the first 2. You can split it with the person next to you, but find the formal charge of the 3 atoms in both of the first 2 structures. Okay, let me zoom in a little for you guys. So find the formal charge of the elements in these 2 structures. You can split it. I'll do the third one for you, and I want you guys to figure out which one is the best structure. Oh. Yeah. Huh? I don't like animals in general, other than eating them. But I see the utility in dogs, for hunting, for whatever, for defense. I'm pretty utilitarian, and so I like to see the function in things. I legit do not see the function in having a cat. Cat's a leech. It just takes your resources. It really is.
Cat's Minecraft though.
Yeah, I don't play Minecraft, but yeah, I don't like either. But I think dogs have more utility, so I like dogs better.
That's why you should get tigers.
You can't domesticate a tiger, Molly. Did you hear about that one Las Vegas perform? Actually, this might have been before you were born, but when I was a kid, it was on the news. Some Las Vegas like tiger performer guy, he like lived with this tiger since it was a baby, and then like trained it, and then he like slept with it. It was like his like best friend, and then they were playing one day, and the problem is that tigers don't know that if they bite you, you die. So it bit the trainer, and the trainer died, and they had to kill the tiger. And so that's why we can't domesticate a tiger, for your safety and the tigers. That's why you also can't domesticate a bear.
There was that one jaguar that put its
Yeah, but they don't domesticate them still. There's like they have a relationship with it and whatnot, but it's still not domesticated. It's still wild. And you'll play with the bear will swat you and kill you. So that's the problem.
I will make my senior quote right now.
That's why you can't domesticate big carnivores. If you notice, all the big animals we domesticate are herbivores or smaller carnivores. Because I will body a dog.
But depends on the dog. Because
True.
hear me out. Like, have you ever seen those pictures of those really swole-ass pit bulls?
Yeah, but I'll still body that thing. It might lockjaw and kill me, but I'll dig its eyes out and still take it with me. Anyway, enough about Mr. O'Body dogs. Let's move on. Okay, so I'm gonna go through this quickly and then let me know if you guys have any questions. But the formal charge for the first one, nitrogen is -2, carbon is 0, sulfur is 1. We good with that? Okay. The second one, nitrogen is -1, carbon is 0, and sulfur is 0. Everyone got that? I didn't make any mistakes this time, right? Okay. The only mistake was coming to school today. Okay, moving on. Let's figure out which one is the dominant one. So we always want to look at the one that is the most electronegative, right? The rule is either everything is 0, but obviously none of these are all 0. So we can't use the first rule. We want to make sure that the one that is the most electronegative is the most negative. Okay, so which one of these is the most electronegative element? N, C, or S? Yeah, N. N is the most electronegative. Okay, and the reason why N is the most electronegative is because even though S is more to the right, N has fewer amount of shells, right? And if you guys remember, the distance between the nucleus and the valence electrons matters a lot more than the number of protons that it has, okay? And so N is actually the most electronegative. So we want N to have the most negative charge. So in which of these structures does nitrogen have the most electronegative charge, or the most negative formal charge? The first one, where it has -2. So that means the best structure, the dominant structure, will be this one right here. And if you even look at it, just kind of without doing any of this, you can kind of see this one makes sense, because if nitrogen is the most electronegative, it wants the most electrons, right? If you take a look at it, the one on the left, nitrogen is sharing the fewest electrons, right? If it's electronegative, it's selfish. It doesn't want to share electrons, so it's only sharing 2 here, whereas these other ones it's sharing 4, here it's sharing 6, but here it's only sharing 2. Okay, so that's how you use formal charge. Any questions? All right. Let's move on. So we're going to move on from formal charge to something called resonance structure. So I know that we're learning covalent compounds, but there's so many little things that go into it. But resonance structures are basically when you have a molecule, sometimes even with formal charge, you can't only use one Lewis structure to symbolize that compound. So ozone is, we have an example with ozone, O3. Okay, God bless you. So you can use 2 different Lewis structures with the same formal charges to describe ozone. So here, let's if I give a number to these oxygens, right? Let's say this is oxygen 1, this is oxygen 2, this is oxygen 3, okay? 1, 2, and 3. Now, we can have the exact same structure with the exact same formal charges, but still have different, resonance structures. Because here, the double bond is between oxygen 1 and 2, right? But you can also draw basically the same structure where there is a double bond between oxygen 2 and 3. Do you guys see that? One of the double bonds is between 1 and 2. The other double bond is between 2 and 3. And these are basically the same structures. However, the double bond just is between different elements or different atoms that are the same element. Okay. Now, the placement of these atoms in these two alternative but equivalent Lewis structures is the same. The only difference is where the electrons are placed. And we call these structures resonance structures. Okay, so these two are resonance structures with one another. Okay. And a resonance structure is basically where you have the same formal charges, you have the same organization, but the placement of the electrons can be between different elements. Okay, and so we call these 1.5 bonds. What's up? Huh? Yeah, go ahead. Okay, now the way that we would draw a resonance structure is like this. We would draw all of the oxygens again, but instead of drawing a double bond, because we can't draw a double bond for both of them, right? That's a different structure completely. We draw something called 1.5 bonds, okay? Because in real life, the double bond doesn't stay in one place. Remember, the electrons are always moving, right? So they're actually moving in between the resonance structures. It could be here sometimes, but usually they're more evenly spread out. And so the way that we would draw these 1.5 bonds is we draw a dotted line to show where the electrons would move in between. So this would be the resonance structure for O3, represented with the 1.5 bonds. Okay. Unfortunately, reality is a lot more complicated than, these nice Lewis structures. And so we have to use these resonance structures. Okay, so with that being said, we are going to end with one final problem. This is what we're going to close off with today. And we're going to close off by drawing the resonance structure for two resonance structures for formate, which is HCO2 minus. Okay, so I'll give you guys about 2 minutes to draw that. You're going to be drawing two different structures. And then if you can, try to draw it with the 1.5 bonds as well. So draw the two resonance structures for formate HCO2 minus. All right, I'll give you guys another minute to draw the two resonance structures. And we'll be done for today. Huh? Yeah, I think it's meant right. 5:30. Yeah,
5:30 already.
I wish. All right, you guys ready to go? Yeah, all righty, let's do formate and then we will be done. Okay, so resonance structure for formate. First thing you want to do, as usual, is you want to count up the valence electrons. So I'm not going to be asking you step by step anymore because hopefully you guys get it. You'll have 1 for the hydrogen, 4 for the carbon. There are 2 oxygens, so that's 12 plus 1 more, and that is going to give you a total of 18, right? Okay. We want to put carbon in the middle and then H on the outside. And since oxygen is more electronegative, oxygen also goes on the outside. We are going to put single bonds between all of them. That's going to give us 2, 4, 6. It's going to get us down to 12. And then we want to make sure that we complete the octets. So we're going to put 2, 4, 6, 2, 4, 6. So we've used all the valence electrons, but if you guys notice, carbon does not have its octet, right? So what that means is carbon needs to form a double bond with one of the oxygens, and that's actually going to give you your resonance structure. Because carbon can either form a double bond with this oxygen right here, right, like this, or it could form a double bond with the other oxygen. So we can have oxygen right here, form a double bond with the carbon instead. Okay, so either way, it's basically the same. If you guys do the formal charges, you'll see that the only difference is that the formal charge of the oxygens are going to switch. So if you guys wanted to draw the 1.5 bond, what you could have done is H bonded to C, and then 1.5 bonds between the oxygens and the carbon like that. Okay. Oh, and make sure you guys do the minus sign, brackets minus. Okay. Any questions? Okay. So yeah, just a lot more things to kind of keep in mind about the same thing. But I think practice is probably the best way to do it. And we should be able to finish unit 9, not the next time we meet, but the time after. So next week. Okay. Alrighty, guys. Good job today. I'll be posting this online if you guys need it. But good luck on your homework.